Welcome to our lecture online. Our next example is again a gate underneath the water, but instead of having the hinge at the bottom of the gate, we now have the hinge at the middle of the gate. Notice the gate has a width of 10 feet and a height of 6 feet, which means that the water pushing against the gate, the water being behind the gate, and the water goes all the way to the very top of the gate, will push the gate in a clockwise direction, looking from this direction, and the water at the bottom will push the gate in a counterclockwise direction. So the resulting torque will of course be one minus the other. So how do we deal with that? Well, we're going to need two integrals, one for the top part of the gate and one for the bottom part of the gate. And so to do that, we're going to need two small segments that we're going to consider, one at the very top and one somewhere at the bottom. Because we're going to have two different distances, let's call that d top and d bottom, the distance to each of our segments. And so you can see that we're going to need different equations to do that. So first of all, let's do the top portion. We're going to get the top torque. And so to do that, we need the force on this. It's going to be a small amount of force, dF, which is going to be equal to the pressure at that point times dA. And the pressure at that point, that's going to be a distance y below the surface. So it's going to be rho gy, that's the pressure at that point, times dA, which is the width, times the height, which is going to be a dy. So W times dy, that's the force on that small little strip from the water behind it. Then the torque caused by that will be a d torque, is going to be a dF times d at the top. And so that's going to be equal to rho g y w dy. And the distance at the top, well, let's see here, that's going to be 3 feet minus y is going to be this distance. That's going to be 3 minus y. It looks like to get the torque at the top, we're going to need two integrals, because the torque is going to be the integral of all the d torques, and we're going to integrate from, well, let's see, from y equals 0 to y equals 3, from 0 to 3, and it's going to be equal to the first integral, which is 3 rho gw times 3 times the integral of y dy from 0 to 3. That's the first part. Now the second part is going to be minus rho gw times the integral, we have the minus already accounted for, y times y, which is y squared dy from 0 to 3, because from y equals 0 to y equals 3 for the top portion. So let's go ahead and calculate that torque. And of course, the clockwise torque, we're going to end up with a negative answer. So this is torque at the top. And so we're going to take that amount, and that's going to be a clockwise torque or a negative torque. So calculating this, we get torque at the top is equal to 3 rho gw times y squared over 2 evaluated from 0 to 3 minus rho gw, we don't have a 3 there, times, let's see here, times y cubed over 3 from 0 to 3. All right, that we can evaluate. Let's go ahead and do that. So that means torque at the top is going to be equal to, when we plug in the upper limit, we get 9 squared divided by 2. Let's plug in all the numbers, see what we get. We get 3 times rho times g. Now, of course, in British units, we're going to have the density times g, which is 62 pounds per cubic foot. So that's pounds per cubic foot, pounds per cubic foot. That's rho times g. W is going to be 10 feet, 10 feet. And then we have y squared over 2, that would be 9 over 2. That would be 9 over 2, that would be feet squared, like that. Minus rho times g, which is 62 pounds per cubic foot. We have w, which is 10 feet. And then we have 27 divided by 3, which is 9, minus 9 feet squared. 9 feet, let's see here, 3, that would be 9 feet cubed, 9 feet cubed. All right, so I think I'm off on something. Let's see here, the top, unit-wise. Feet, we have Y. So this is feet. So this, I was missing a unit. So this is 3 feet, not just 3, so that the units come out to be the same. So now we have foot-pounds as torque. So torque at the top is equal to. Now with a calculator, we'll be able to figure out what the value is. So we have 27 divided by 2 minus 9, everything else being the same. So that would be 27 divided by 2, 13.5 minus 9, which is 4.5, times 62 times 10, that gives us 2,790 foot-pounds. 2,790 foot-pounds. And so that's 620, that's 620 times 4. Yep, that's about right. Okay, we're in the ballpark. How about the bottom? So now we need torque at the bottom, which is going to be the integral of, and actually, I think I'm getting a little ahead of myself. Well, no, it's going to be an integral of all the d-torques, which is equal to, at the bottom, we're going to integrate from y equals 3 to y equals 6. So we're only going to have one integral because the distance d is coincident with the value for y. So again, we're going to have the d-torque, which is going to be the density times g times y, times w, that's all the same, times dy. So that's going to be the torque on a little strip. Now the distance d is going to be y plus, so it's going to be y minus 3. Ah, that's right. Because if I go from here to here, that gives me y. If I subtract 3, I get the distance d. So it's going to be times y minus 3, because that's going to be the distance from here to here. It's going to be the total distance. Y minus 3 gives me the distance from the hinge to the bottom to the strip. Looks like two integrals again. Oh well, that's how it goes. So this is equal to the integral of that. So let's go like this. Oh, I think I got it in the wrong place. I need it like that because I need to include the y here. So pull out all the constants. We have density times g times w, density g, w, and then we have times the integral of y squared dy minus 3 times the density times g times w times the integral of y dy. The negative is taken care of, and so we're going to integrate from y equals 3 to y equals 6, from 3 to 6. It's a little bit more messy than I was hoping for, but let's go ahead and move ahead. So this will be equal to the density times g times w times y cubed over 3, evaluated from 3 to 6. And that would be minus 3 density gw times the integral of y squared over 2 from 3 to 6. So I'm going to get a lot of things in here. So let's get the numbers in. So density, I can probably factor out a rho gw. So rho g is 62 times w, which is 10. Okay, so I factor out a rho gw from both. Then here, when I plug in the upper limit, I get 6 cubed, which is 216 divided by 3, minus 27 divided by 3, minus upper limit, that would be 36 divided by 2, and a minus times the minus would be plus 9 divided by 2 times 3. Did I forget about my 3 here? 3 times, I think I did. I got to be careful. Can't forget my 3. So it's 36 times 3, that would be 90, that would be 108. So 108 divided by 2, minus 108 divided by 2, and minus times the minus is plus. So I have 9 times 3, which is 27, divided by 2. Okay, now I think I'm set. Should I go ahead and simplify that a little bit? Probably can. So let's see here. We have 216 minus 27. Divide by 3. That's 63. So it would be 620. I have 216 minus 27 divided by 3, which is 63, minus, okay, I have 54. So 108 plus 20, okay, let's see. Minus 108 plus 27 divided by 2 equals, that would be minus 40.5. Okay, subtract that from 63, so plus 63, and then multiply times 620. And that means I have a total torque equal to, that's from the bottom, that would be 13,950 foot-pounds. That's torque at the bottom. Do I have a torque at the top? Right here, torque at the top. And that means the torque at the bottom wins, so I have to subtract the torque from the top. So torque at the bottom minus torque at the top is going to be equal to 3950 minus 2790, which is equal to 11,160 foot-pounds for the total torque on the gate. Remember, we have to differentiate between the torque at the top and the torque at the bottom. And that is then the answer. That's how it's done.